Hey everybody, this is our video solution to Quiz 9. This is from Fall 2021, Math 106. It's our Integral Calculus and Differential Equations course. There's only one problem, that's why it's solution. So this is the one and only problem, and what we're doing is trying to find a solution to this differential equation, and we would like to use power series to do it. So what that means is that we're going to assume that y has a power series. And so we'll usually write it as some infinite series, right? We start at 0. The coefficients we'll call a sub n. And then since it's a power series, we multiply them by x to the n. Now, a good justification for making this assumption is that, well, this is a nice second order differential equation. And we actually could apply Fuchs theorem in this case. So Fuchs theorem, apologize, put the apostrophe in the wrong spot. Fuchs theorem is telling us that when we have a second order differential equation of this form, then if these functions p and q have power series that are convergent on some interval, then we're going to be able to find a power series solution for the differential equation, which also has that radius of convergence. Okay. In this case, there is no y prime, right? So the p is 0. So it's 0 in our case. And for, there's supposed to be a qy here, excuse me. The q, right, is x. And x, yeah, it definitely has a power series expansion, right? It is its own power series expansion, right? You make 0 all the coefficients except when n is equal to 1. And then you make a1 equal to 1. And of course, that converges everywhere. So y should converge, right, for any x value, right, if we find this power series solution. And all we have to do is plug it into this second order differential equation. So when I take a second derivative, I'm going to, let's see, two derivatives means I will get rid of the first and second terms, right, the constant and the linear terms. When I take two derivatives, first I bring down an n, then an n minus 1. So the n minus 1 second, we had the n first, a sub n, x to the n minus 2. Okay, plus, okay, now y we've written here, but we're multiplying it by x. So when I multiply by x, it's going to increase the exponent on x by 1. So this will be a sum starting at 0, a sub n, x to the n plus 1. All right, well, I'm not super pleased right now because I want to put these together and I can't. These aren't lining up correctly. So what I'm going to do is re-index. All right? And remember the rule is if I want to increase my n in my sum, I have to decrease my index. Okay, so this will now be, since I want to increase my exponent by 2 to make this x to the n, then I'm going to decrease my index by 2 down to 0. Okay, now all the n's go up by 2. So n minus 1 becomes n plus 1, n becomes n plus 2, a sub n becomes a n plus 2, and then we have x to the n. All right, now this one I want to decrease my n by 1. All right, I want to make this go down to n, which means I need to increase my index by 1. So this will start at 1. I have let's see, n minus 1. All right, I'm decreasing my index by 1. And then, whoops, I have x to the n power. Now I can almost put these together. The only issue I have is that this one starts at 0 and this one starts at 1. I want them both to start at the same place. So basically I need to peel off the n equals 0 term. So if I peel off the n equals 0 term, let's see, when n equals 0, I get 0 plus 1 and 0 plus 2. So 1 times 2 is 2. and then 0 plus 2 is 2, so 2a sub 2, and then x to the 0 is just 1. So the very first term will be 2 times a2 plus, now I can put the rest of these together starting at 1. And let's see, we're going to get n plus 1 times n plus 2 times an plus 2 plus an minus 1, and all that gets multiplied by x to the n. All right, now we know that this power series on the right is equal to 0, which is its own power series, which means that every one of the coefficients that we see has to be 0. Okay, so this follows from the power series uniqueness. We know that 2a2 has to be 0, and we know that n plus 1 times n plus 2 times an plus 2 plus an minus 1 has to be 0 for n at least 1. Well, this first one, that's great. Divide by 2, and you know that a2 is equal to 0. Easy enough. What about this next bit? Well, let's solve for an plus 2. So an plus 2 is going to equal negative an minus 1 divided by n plus 1 times n plus 2. And again, this is for n at least 1. Cool. Now I check. I have an n plus 2 and an n minus 1. Those differ by 3. That means I'm actually going to have 3 cases here that I'm going to be looking at. Okay, so let's start working. So we know the very first one is an A0. All right, fine. Then we are going to have an A1, and then we're going to have an A2. And A2 is equal to 0, which is great. That basically means this whole column is going to be all zeros, right? Just jump ahead. 3 forward would be A sub 5. A sub 5 is going to be negative a sub 2 over n plus 1 times n plus 2. Okay, what's n plus 1? N plus 1 is 1 less than 5, so that'd be a 4 times a 5, because there's your n plus 2. But it doesn't even matter what's on the bottom because a2 is 0. So that's a 0. All right. And so we're going to keep going down, and anything that looks like this, 2, 5, let's see, the next one would be an 8, right? Then an 11, like they're all going to be 0. And so the generic thing, right, would be, well, let's see, they differ by 3. So I could write 3 times some k or some n, whatever, and then it's 2 more than a multiple of 3. So anything of that form, 3n plus 2, right, the a is going to be 0. So we're really only interested, right, in these other cases. So let's see, the next one would be a3. And a3, let's see, so that's going to be negative. And we go back by 3, so it'd be a0 over. Okay, we copy the 3, and then 1 less is a 2. Okay, fine. Let's go 3 forward. That'd be a6. a6 is going to be negative a sub 3 divided by, okay, we copy the 6. We go back 1, we get a 5. And now I know that the a sub 3 I can rewrite using this expression. So negative a3 over 5 times 6. Nope, sorry. Write the 1. The a3 becomes a negative a0 over 2 times 3. Let's put this together now. Negative and negative is a positive. I still have an a naught, which I might as well just stick on the side. And I have 5 times 6 times 2 times 3. Ooh, that's interesting. So let me write it kind of decreasing. 6 by 5, and then 3 by 2, and then we have an a naught. Interesting pattern. All right, let's keep going. The next one would be a9. That'll be negative a6 over, copy the 9, go down by 1 to give myself an 8. Now I can replace the a6 with the expression we had above, and that'll be negative 1 over 9 times 8, 6 times 5, 3 times 2, a naught. All right, I think I'm starting to see what's going on. First, there's an alternator. All right, we have, well, the a naught doesn't have a negative, but there's a negative, then we get a positive, then we get a negative. So if we're trying to write down the generic one. And what do these all look like? 0, 3, 6, 9. They're all multiples of 3. So we can write it as like 3 times n. So the very first thing is there should be an alternator. And of course, there's a question, should this be an n or an n plus 1? And let's see. We have a negative when it's 3 times 1. We have a positive when it's 3 times 2. We have a negative when it's 3 times 3. So when the n here is odd, we get a negative. So I better put an n. Okay, then I get 1 over, and let's see, the very first thing I see, I'll get like a 3n times 3n minus 1. And then it looks like I jumped down, right? Ooh, this is going to be tricky to write. 3n minus 3 times 3n minus 4. Ew, gross. And we keep going all the way down until we get to 3 times 2. And then we'll have an a naught. All right. Well, I wonder if there's a nicer way to write this. And I think what makes it annoying is we're missing some stuff, right? We're skipping some things. Could I put those things back in? That might make life a little bit easier. So what am I missing? Well, let's look back at this previous one. I'm missing on the bottom the 7 and the 4, and if you like, even the 1, right? So what if I put those back in? If I put in a 7, a 4, and a 1, well, I have to put them in both the top and the bottom. But if I put them into the bottom, then I just get 9 factorial, and that's a lot nicer. And on the top, well, I have this decreasing product, and they're decreasing by 3. Well, that's what we might call a triple factorial. So what I'm going to do here is, on the bottom, I'm going to include all the extra bits so that I can just make this 3n factorial. And on top, well, what's going to be the number that I start with? Well, it'll be 2 less than this 3n. All right, that's the first one we're missing. 3n minus 1. Oops, we're missing 3n minus 2. And then we do a triple factorial. All right, so that's what we should probably write down here, right? That's definitely a lot easier of a formula to keep track of. Now, why don't we prove this, right? So the proof we're going to do is by induction. So when n is equal to 1, what happens? When n is equal to 1, this formula would give us, let's see, minus 1 to the 1, and then, okay, 3n minus 2. Well, n is 1, so we'd get 1 triple factorial. Woo! And then on the bottom, we'll get 3 times 1 is 3 factorial a naught. And let's see, negative 1 to the 1 is negative 1. 1 triple factorial, that's just 1. 3 factorial is 6 a naught. So let's go back up and look at what our a3 was. A3 is negative, we can rewrite this, 1 over 6 a naught. Hey, negative 1 over 6 a naught, that's what we have. Negative 1 over 6 a naught. Okay, so the base case works. How about the inductive step? So for the inductive step, we assume that this formula works for n, and we want to prove that it works for n plus 1. Okay, so we get to assume a sub 3n is equal to negative 1 to the n times 3n minus 2 triple factorial over 3n factorial a naught. And now let's try to see what happens with a 3 times n plus 1, which of course is the same as a 3n plus 3. All right, well, by our recurrence relation, it's going to be negative a3n over, okay, we'll have a 3n plus 3 and then a 3n plus 2. So this will be negative a3n, right? I go down by 3 over 3n plus 1, right? Or we could write it as 3n plus 3 times 3n plus 2, 1 less. But by our inductive step, right, our inductive hypothesis, we can assume this a3n looks like this expression here. So we have negative 1 over 3n plus 2 times 3n plus 3 times negative 1 to the n, 3n minus 2 triple factorial over 3n factorial a naught. I put these negatives together, and I'll get negative 1 to the n plus 1. And now on the bottom, I have almost 3n plus 3 factorial. You'll notice I have everything from 1 up to 3n. I have 3n plus 2, and I have 3n plus 3. I'm just skipping 3n plus 1. Okay, well, I can fix that by putting a 3n plus 1 on top. Right? So I put the 3n plus 1 on top, then I can have an entire 3n plus 3 factorial, or if you like, 3 times n plus 1 factorial, and then times a naught. But now this piece on top, 3n minus 2 and 3n plus 1, they're 3 away. This is actually the same thing as 3n plus 1 triple factorial. All right, and that's what we wanted to prove, that if I use n plus 1, that I get back the same formula that I'm looking for. Negative 1 to the n plus 1, then 3n plus 1. Oops, we're missing some parentheses, aren't we? 3n plus 1, triple factorial. And then we need to be dividing by the 3 times n plus 1 factorial, and that's what we have. Okay, so we have worked out the coefficients for the multiples of 3 case, right? This is the case that starts with A0. We also have to do it for A1. Okay, let's get to it. So for A1, right, the next one is A4. That's 3 forward. And that's going to be negative, okay, it was A1 over, and then we need to do, we copy the 4, and then we do 1 less as a 3. Okay, let's double check. Did we get the right formula? Okay, you take A4, it would be a negative, and then yep, you go back 3 to A1, copy the 4, go down by 1 to a 3. All right, let's check the next one, A7. So we go 3 forward. This will be negative A4 over, copy the 7, go down by 1 to a 6. Now I can replace the A4. So I have 1 over 6 by 7 times negative A1 over 3 times 4. Okay, and I put these together, the negatives go away, and I'll get 1 over, and, well, by gum, this looks pretty similar to what I was getting before, doesn't it? 7 times 6, 4 times 3 times A1. Oh, so close, right? Before we had 6 by 5 and 3 by 2. Okay, but it's still pretty close, right? It's still the same idea, and it should help us spot the pattern easily. Okay, what's the next one? 3 forward is A10. That'll be negative A7 over 10 times 9. Now I can replace the A7. So I have negative 1 over 9 times 10 times 1 over 7 by 6 and 4 by 3, A1. Put these together, and we have negative 1 over 10 times 9, 7 times 6, 4 times 3, all times A1. All right, I think I see the pattern now. We're getting the alternator again. We always have a 1 in the numerator. And we, again, have these pairs, right? We're multiplying up. We're skipping stuff, right? We skipped a 2, we skipped a 5, we skipped an 8. So why don't we put those in, right? What if I did that? What if I made this negative, and I'll put a 2, a 5, and an 8 on the top. That way I can make this a 10 factorial on the bottom. And that actually gives me the pattern, right? So what do these all look like? Well, they're not quite multiples of 3. They're one more than a multiple of 3. So these all look like 3n plus 1. And this should be something like, let's see, we're going to need an alternator. And let's see, now if this is 3 times 3 plus 1, The n here is odd, so okay, we're going to do the same thing, negative 1 to the n. Let's see, now looks like I take this 3n plus 1, put it on the bottom, and give it a factorial. And then what's happening on top? Well, I again have this product. Everything differs by 3, so we're talking about a triple factorial. And where does it start? Well, it's starting 2 less than where we are, right? And this one up here, let's see, we'd be putting in the 5 and the 2. Again, that's 2 less than the 7. Okay, so what's 2 less than 3n plus 1? Well, it's 3n minus 1. So we start from 3n minus 1, and we do the triple factorial, and then multiply by a1. Okay, let's do the proof. Okay, again, this will be by induction. So when n is equal to 1, what happens now? Let's see. We should be getting, let's see, let's write this down, negative 1 to the 1. All right, when n is 1, 3n minus 1 is 2. So we'll get 2 triple factorial over, okay, 3n plus 1 is 4. So we get 4 factorial times a1, which is negative, okay, 2 triple factorial is just 2. 4 factorial is 24. a1, we could simplify and get negative 1 over 12 times a1. Well, let's take a look at what our a1 was. Oh, or not sorry, that's not our a1, it's our a4. Yep. And look at that, this is negative 1 over 12 a1. Beautiful. Okay, so then this was equal to a4. So it works when n is equal to 1, right? Remember, this is 3 times 1 plus 1. All right, now let's do the inductive step. All right, so for the inductive step, we assume that our pattern is correct for n, right? So 3n plus 1, 3n plus 1 will be negative 1 to the n times 3n minus 1 triple factorial over 3n plus 1 factorial times a1. All right, so now what happens when I make n plus 1? So now I get 3n plus 1 plus 1, which is the same thing as 3n plus 4. Well, by our recurrence relation, this is negative 3n plus 1 over, okay, we copy 3n plus 4 and then do 1 less 3n plus 3. But by our inductive hypothesis, we know that a 3n plus 1 is written in this way. So I have negative 1 over 3n plus 3 times 3n plus 4 times negative 1 to the n 3n minus 1 triple factorial over 3n plus 1 factorial a sub 1. All right, let's put them together. Again, the alternators combine. So we get an n plus 1. Let's see. Now, on the bottom, yeah, we have the same deal, right? I factorialed all the way up to 3n plus 1. I skip 3n plus 2, go to 3n plus 3 and 3n plus 4. So let me fix it by putting in a 3n plus 2 so that I get an entire 3n plus 4 factorial on the bottom. And now, because 3n plus 2 and 3n minus 1 are 3 apart, I can just combine these into one triple factorial, namely 3n plus 2 triple factorial. Okay, and that's what we were hoping for. Right? We wanted it to be that when you looked at the n plus first term, that you got an alternator now to the n plus first. We wanted this numerator to be 2 less triple factorial. Well, 2 less than 3n plus 4 is 3n plus 2. And we wanted the denominator to match and be the factorial. And sure enough, 3n plus 4 factorial. It matches. Whew, okay, so we've done that. So now let's go back up. What were we doing? Like it was so long ago. We assumed that our y had a power series solution. And now we needed to figure out all these coefficients. And so we have figured out that there were 3 cases to look at. A third of them, basically, I'll give you 0. And then there were the a0 and the a1 cases, namely the multiples of 3 and the one more than a multiple of 3. And we now have formulas for those coefficients. So let's put that all together. So therefore, our y is equal to, so let's do the multiples of 3 first. So the multiples of 3, okay, there was our a sub n, right? It's going to be negative 1 to the n, and then, okay, all this stuff. And that'll be multiplied by x to the 3n. Okay, so we have negative 1 to the n, 3n minus 2 triple factorial over 3n factorial. And then there was this a naught, which we can pull all the way outside, x to the 3n. Okay, that gives us all the ones that are multiples of 3. How about the ones that are 1 more than a multiple of 3? Well, these were all minus 1 to the n. And then we had 3n minus 1 triple factorial over 3n plus 1 factorial, x to the 3n plus 1. Of course, there was this a1, and we pull that out. So these are our constants. That's how we know we have a nice family of, right, a general solution. And this is our y. And yeah, it's a little bit crazy looking. Yeah, it's not so obvious, right, what elementary function maybe this corresponds to. Okay, but this is how we can do it. Yeah, it's a lot of work, right? It's a lot of work. Pay attention to those details, and yeah, hopefully I didn't make any mistakes, right? Maybe I did. There's a lot of work in here, right? So if you see a mistake, tell me about it in the comments. All right, have a great day, everybody.